But now, at the very end of class, we're going to talk about direct proofs real quick. I was going to do one for you. Direct proofs. This will be so simple, it's not going to seem like it's crazy, but it is. So first of all, let's talk about a definition. So the definition of the evens. An integer n is even if there exists an integer k such that n equals 2 times k. Basically saying you're even if you're a multiple of 2. But this is the official way to write it, right? Another thing you can say is that n even is equivalent to there exists a k and z such that n equals 2k. Kind of cool. Anyway, claim. Really simple claim. The sum of any two evens is even. Which, how can we write this in our mathematical notation?
Can you like define a domain of even numbers and multiply by 2?
Yeah. So what you say is for all n, I'm just gonna write the evens for now. That's fine. Such that, or sorry, not such that, maybe there's before. And for all m, and even. So this is a double universal statement. The sum of any two even numbers is even. That means for all n evens, for all m evens, for any two evens you pick, you add them together and you get even. Okay. Here's the proof. This is not going to be mind-blowing, but it should be. Notice that this is a for all proof, right? It's a universal statement, like where this is your predicate right here. The way how do you prove universal statements? Right now, the only way to know how to prove it is method of exhaustion. But that will be particularly exhausting here. Why? Why will method of exhaustion not work?
There are infinite even numbers.
There's infinitely many evens. So we can't simply write down all the evens. And if you really think about this, right? I think we all know in our bones. We all know deep down this is a true fact. But why is it a true fact? Why do you know that? Like before you took this class, someone asked you, is sum of any two evens even? You've been like, yeah. Why would you say yeah?
Well, in this case, I think if n is defined as like 2
whoa,
times
whoa,
k.
No, not this case, or before this class, right? Before all this beautiful notation, everything we had, you probably thought the sum of two evens was even, right?
Okay, I mean, you can draw out like even things, right? And they'll be in 2 columns. And if you add another 2-columned thing and it's even on top, right? It'll stay even.
That's
Right?
maybe
Like
a good way.
graphical
That's
example.
maybe a good way to think about it. But once again, it's like, how do you draw? Like I think what Alex is saying, right, is like 4, right? You can think of as being like this column plus this column. It's even because you can split it into 2. And,
right, and each column's like basically k here. But...
And then 6, you could write it like that and that, right? And then 4 plus 6, just add the columns together. You can still split into 2, you're fine. But once again, it's like we're kind of doing that for particular examples. We didn't draw every example possible. That's kind of a more beautiful method of exhaustion, what you're talking about there, right? How do we prove for all of them at once? That's the big key. It's like we all know this is true, but can anyone really tell me why it's true? Yeah, like one of those weird thought experiments where it's like you sold your soul to the devil, and he's like, oh, you can get out if you can prove this. It's like how do you actually prove this beyond any doubt that all of these infinite numbers, there's like that even 1 trillion whatever, if it's even, you add to another giant number, it's still going to be even. Without just going, I work for 2 or 3 examples I tried, so it's going to work forever. Which, by the way, is exactly what 2C in the homeworks was to make you think about. Trying a few examples might not always work. So here's the idea. Instead of proving, right, that this will work for any particular n and m's you plug in, instead of just doing n and m's and checking, so instead of checking that n plus m, this statement is true for any n and m, that's really what we're doing, right? We're checking the statement is true for any n and m. We can take advantage of this predicate thing. You can say, remember, predicates are like properties, right? Instead, let's try to show that any 2 numbers with the property of being even will have the property that when you add them together, they'll also be even. It's just the properties. It has nothing to do with the particular statement. So, proof. Consider n and m even. Then, by definition, right, if you're even, that means there exists a k, so this works. There exists a k1 in z and k2 in z, such that n equals 2k1 and m equals 2k2. Right? That's just by definition. We have an even n and m. Instead of looking at particular ones, we just know that if you're even, you have the property, you can be written in this way. But then, n plus m equals 2k1 plus 2k2. And then what can we do?
We can distribute our undistributes.
Yeah, undistribute factor, right? Exactly. Factor that too. This equals 2 times k1 plus k2. Note, since the integers are closed under addition, that just means if you add any 2 integers together, you get another integer. We're going to talk about that next time. K1 plus K2 is in Z. So K1 plus K2 is itself an integer. So then we just wrote n plus m as 2 times an integer. Thus, n plus m, which equals 2 times K1 plus K2, is even by definition for any n and m evens. Square. We are done. That's the end of class. Oh wow, wait, my bad. Got excited about direct proofs. But the point is, we're doing one the next time. I just wanted to give you guys a taste. These are direct proofs. This seems super, almost stupid simple. Wait to think about how powerful this is. We just proved something about infinitely many things. Actually, infinity cross infinity, right? Order pair of infinitely many things. In like 3 sentences. Because we didn't look at any of them individually. We didn't look at statements. We instead looked at properties. The property of being even means you can be written this way. And then being this way has the property that by the distributive property can be added to get 2 times this, which has the property of being even itself. We are just linking together properties, not statements, right? This is the whole P of X implies Q of X versus P implies Q. These linked properties, these linked statements, linking properties is much more powerful. Linking properties is what allows us to do this. Yes. I hope that's got to give a little bit of goosebumps or something if you really think about it. We're going to prove much more complicated things. This is so simple. But the point is, I think simple almost makes it more interesting. Like a complicated, the fact that a complicated claim, you kind of would think would have a complicated proof. A simple claim, I want you guys to see that the sum of any two evens is even. That's not as simple as you think it is. That's an infinite statement. That's actually incredibly hard. Anyway, that's class. Any questions?
One of the
Go first.
one of the quizzes was for section 4. Is that one still on, or?
Oh, I'm gonna take that out. We didn't get to that. My bad, guys. I'm gonna take section 4,
Okay.
4.1, or I'm just gonna make the due date next Friday. Yeah.
So I guess my question was, how do you go about proving closure?
Excellent question. And this is where I turn the recording off. But yeah, let's talk about it.